No? Okay. I will then.
We're just catching up.
I know.
Even though I see Sam like every day.
And you want us to go through like
You know, yesterday. What?
Okay, so everybody have a good break? Everyone more time? Yeah, I want more time too. Okay, so I gave you the mind-altering assignment of analyzing the regress.dat data. And in there we had a number of times somebody went to a doctor and we wanted to model that as a function of mental health, physical health, and some self-reported level of stress or something like that. What I'd like to do is have you guys lead that discussion and talk about what it is that you guys did, why you did it, because remember that was the assignment, is to write down what you did, why you did it, what your thoughts were, you know, sort of in a stepwise fashion. So who'd like to start? And by the way, my solution to the problem is I've put that out there. I also put it out. I'll put it out on Blackboard at other costs too.
So I guess I can.
Okay, you can
since
start.
It's easier to start. So when I first got the data, I just did like a describe function and summarize function just to take a look at it, just to like look at the number of observations, variables, storage type of the data, and then like the variables and observations for each variable, just to make sure that nothing was missing, I guess. And then also to look at some of the descriptive statistics, like the mean standard deviation, min and max, to see if there was any crazy outliers or anything that didn't look normal that I wouldn't expect it to have.
Did anybody plot the data? Histograms, density plots, or anything like that? That's always a good idea too, is to use the visual cortex to do that. That's good. I got the look. You give me the look.
Yeah.
Yeah. So you guys had that look up. What the fuck are you talking about? You got that look.
I did it.
You okay? You're cool? All right, cool. Excellent. Anybody else? Anybody do anything different? Anybody not do the sort of the exploratory work first?
I did not.
You did not.
I
Okay.
just went right for it.
Pardon?
I just went for it.
You went for it, right? Okay. It's a good idea to do the exploratory work first. Okay. Let's say, for example, that you have an exam in class or something like that. It's always a good idea to do the exploratory work first. Hint, hint, wink, wink, nudge, nudge.
Can we run the graph matrix real quick? I just had a quick question.
Well, I didn't get that first. Okay, so we'll do this sort of step by step if you want. In my code, I pretty much did what Susan did, but that's sort of not fair because we sat and talked about it. And the other thing I did was I sort of did this histogram, put my histograms there. Anybody notice anything different about our data? Anything strange about our data? Particularly our outcome variable?
That it's skewed.
It's very skewed, right? And the other thing is let's think about the kind of data it is, right? It's the number of times somebody went to the doctor, right? So, right, by definition, if I were to do a linear regression, multiple regression, that means that my outcome variable could take on any value from negative infinity to positive infinity, right? Does that make sense? Like I could predict a negative number. Is it possible to come up with a value less than 0 for a number of times been to the doctor? Okay. All right. Did anybody sort of think about that? It's okay if you didn't. I mean, that's why we're here, right? Because I selected these data purposefully to help tell a story. Okay. And you want to go on next to the correlation matrix?
So when we see this, that it's really skewed, you had mentioned something in the last class that it's not necessarily your outcome variable that needs to be in a
Right.
normal distribution, it's
Right.
the residuals.
Right.
So I just wasn't sure when I saw this and some of the other graphs. In my mind, I didn't automatically say this is something I need to look out for down the line. And I
Right.
just want to make sure I'm not missing
Right, yeah, so it's
anything.
our errors that we assume to be normally distributed.
Mhm.
But what we have here is we have a value. Our data by definition are integer data.
Right.
0 to positive infinity. And it's possible that in our regression that I didn't look at it, I didn't look at our predicted values, but it's possible for us to come up with a y hat of less than 0,
Right.
which is out of domain. Right? That doesn't make sense. So it's just something to think of, the quality and the nature of the data. Because the fact that these are count data, actually there are consequences to this in this specific data set. That can you guys see the scatters there, or are they too small? Can you see them okay? No? Okay. The other thing you'll notice in my code here is I've started to introduce the concept of loops to you in my code. So we'll go over that in Stata Lab tomorrow. Better? Okay, so here's our scatter plot matrix. Any observations, any comments here?
So this overall was supposed to be to eyeball if there's a high correlation between any of the two variables. The way I interpreted this is that there wasn't, except for maybe Menhiel and stress, and maybe
Okay.
there was something there.
Okay. Well, I look at the middle one on the bottom, and that kind of, if I were to sort of imagine a line, I might imagine a positive slope between stress and physical health too.
Okay.
And it looks to me that they're all somewhat correlated. But the other thing that I'm interested in looking at is that first column too, right? I'm interested in the bivariate relationships between each of the predictors and the outcome. Why would I be interested in looking at the bivariate relationship between each of the predictors and the outcome? I want to see if they're related, right? Because if I include a predictor that's not related to the outcome, but is correlated with the other predictors, what could that be a symptom of? Not collinearity, but suppression. Right? Suppression. And that suppression is going to exaggerate the relationship that you see between a predictor and the outcome. And if it exaggerates the relationship, the inference is improper. It's not quite valid.
Can you just repeat that again? So if there's a relationship between...
Okay, so let's say I'm looking at the relationship between mental health and number of times I've been to the doctor. Right? So mental health, number of times been to the doctor. So that's this plot here. Right? I'm interested to see if this, for example, if this has a relationship with the outcome variable. Because if it has no relationship with the outcome variable, then it's possible that mental health becomes what we refer to as a suppressor variable. So if I were to draw it using a Venn diagram, it would look like this. So here I have my y, here's an x1, and here's an x2. So here we have x2, which is not related to the outcome, but is related to another predictor. So x2 is suppressing the variance in x1, which doesn't change the absolute size of the relationship between x1 and y, but it changed the relative size of x1 and y.
you want to see the relationships between the outcome variable and the
Yeah.
other variables.
Yeah. Otherwise, what's the point of including it in the model?
What would you say about the top one?
Yeah.
That's the relationship between physical health and number of times been to the doctor. It's not random. Yeah, there's probably a positive relationship, and being able to make that assessment sort of just comes with time and practice, and it's a skill that has to be cultivated. But what I'm encouraging you guys to do is look at the data, and after a while, when you do this, 1,000, 1,000,000 times, it's just like anything else you do, it becomes more intuitive to you. Right? But the other thing that we do, we're going to look at, is we're going to look at those the bivariate correlations too. Right? So if I look at that first column, everything seems to be more or less correlated, positively correlated with number of times been to the doctor. Right? Okay. So nothing too bad here. The bivariate relationships, none of the bivariate relationships are above like 0.8 or 0.85. Right? So the bivariate collinearity seems to be okay here. Okay. Then I'm going to look for the partial and the semi-partials. Okay. So now when I look at mental health, if I look at the squared semi-partial correlation between mental health and the outcome, I see that squared correlation goes down to 0. Right? So what that tells me is that the relationship between mental health and number of times you've been to the physician, or the effect of mental health on the number of times you've been to the physician, is essentially 0 once you've taken into account physical health and stress level. Okay? So it might be interesting to try and interpret that, right, substantively. Okay, and then I'm just going to do my simple regression. Okay. And where did you guys come? I hope you get something that looked sort of kind of like that. And what did you look at first when you looked at this outcome? Did anybody look at the ANOVA table? Yeah, look at the ANOVA table. Then you probably looked at the F statistic coming from that ANOVA table, which was 4303. And by now we know that that's a gigantic F statistic. So our p-value for that overall model is less than 0.0001. So how do we interpret that tiny p-value for that F statistic?
That this model is better than nothing.
This is not a terrible model. Right? It explains a statistically significant amount of variability in the outcome. Okay, now to really interpret our model, we probably want to look at the R-squared. Because we have 468 observations, that gives us a lot of statistical power. So to give us some substantive interpretation as to the explanatory power of our model, you get an R-squared of about 0.22. Right? So how would we interpret that? It's precipitate in that sense too. How do we interpret that R-squared, a multiple R-squared of 0.22?
So the model explains 22 or 21% of the variability in data.
And it explains 22% of the variability in the number of times you've been to the doctor. Right? Is that good? Is that bad? And so just off the top of your head, given what you know about the things that you've studied so far, an R-squared of 0.2 for something that deals with behavior. That's not too shabby. That's actually pretty darn good, actually, right? And we talked about the adjusted R squared. Let's ignore that. How about the root mean square, or MSE is mean square error? What is the root mean square error? We did talk about that.
Standard deviation around the regression.
Standard deviation around the regression line. So if I were to come up with a predicted value, a y hat, right, and I wanted to come up with an approximate confidence interval around my prediction, that tells me that any number that I would predict would be plus or minus 19, almost 20, because I would double that 9.7, right? To get a 95% confidence interval, I would just about double it, 1.96-ish, right? So the root mean square error tells us how much precision there is in our prediction. Right? So the one thing you'll notice over time as you get more into this is that your root mean square error will shrink to 0 as your R squared approaches an absolute, well, a 1. That makes sense. It sort of makes intuitive sense. So the less variability that your model explains, the more wobbly, the more uncertainty there will be in your predictions, which kind of makes sense. But the root mean square error actually quantifies how wobbly your predictions are.
And can you just say that one more time? You double it to...
You double it to get an approximate 95% confidence interval.
Around.
A predicted value. Yeah.
If you had transformed some of the skewness,
Yeah.
that, move on to that.
Well, that's in another lecture, but yeah, go ahead.
I was saying if you transform some of the skewedness, then maybe you'd be able to clean up some of the loss of...
Right. So let's talk about that for a minute. Did you do any transformations?
I didn't do this on that, but then on some stuff that I'm working on, like I have possible size, and it's also like it's a predictor, and it's like totally right skewed. And so if I log transform it, then it becomes more normal. And then I didn't know if that was.
So the question is, so do you understand what we're talking about here? We could transform the data, right? So instead of predicting number of times somebody went to the doctor, we could predict, say, the log number of times somebody went to a doctor. And we could do that. In which case, that might make that outcome, instead of that positive skew that we observed, it might make it a little more symmetrical. Right? The problem with that is that now the model, the meaning of the model, becomes a little less intuitive. Right? It becomes a little less intuitive. Because if you transform things back and forth between logs, and then you were to exponentiate it to get back to the original value, that's not what you modeled. You didn't model the exponentiated log value. So how do you try and communicate log number of times somebody went to the hospital to somebody? It loses that intuitive meaning of the data. Right? So for modeling purposes, if your audience is sophisticated, yeah, by all means, go for it. My assumption is that most policymakers are not that. Thank you. They're not as well trained. They're thereby making the interpretation of the models far more complicated. Okay. Yeah.
Are your answers any different when you do that?
Absolutely.
Or do you just look?
They'll be different because the question you're asking is different. Because instead of asking, how do these things affect the number of times you've been to for how many times did you seek treatment, or let's call it utilization, now it becomes, what is the relationship between these things and the log level of utilization? It's a different question.
But the direction or the trend or whatever should be the same.
Maybe, probably.
It might not be.
It might not be. Right? Because with logs, you can get now you can go into negative land. Right? Whatever, right? All right, so that's how we interpret that root mean square error. It really is a quantification of how stable any given prediction would be. So, right, so think about it that way. How much variability there is in any predicted value. So with a back of the envelope calculation for this would be plus or minus 20 doctor visits. Does anybody remember what the mean number of doctor visits was? 8. 8 plus or minus 20. Not terribly stable. Okay, so now we have physical health, mental health, stress. What are all those things? Now we have a regression table, right? So what do we see? We see that mental health we knew was not going to be significant because those p-values they're going to be exactly what they were for the semi-partials. So we see that mental health has no effect on the number of times you've been to the doctor. But we see that, how do I interpret that 1.8 for physical health there?
For every 1.8 unit increase of physical health, for every one unit increase in physical health, 1.7 increase in doctors.
Expected increase. Right? So remember, the coefficient is, for every 1 unit increase in the coefficient, we expect a slope change in the outcome. Right? In this case, because it's multiple regression, holding mental health and stress level constant. So you want to take a crack at interpreting stress?
So for every 0.013, no.
Backwards. It's good.
For every increase in unit stress, we will expect a 0.013 increase in doctor's
There
visits,
you go.
holding mental health and physical health.
There you go. Good. That's it. Good. How about the constant there, that -3, 7? How about that?
Yeah. Physical health, mental health, and stress were all 0.
Let's stop there for a second. Is that plausible? You don't think it's plausible?
You don't know anything about the scales.
Well, zero is
it is
healthy.
plausible.
The higher the number, the less health you have, or the
Yeah, we
more
don't know.
stress.
Can you actually score a 0 on it?
Yeah, you can. Let's say you can
Sure.
score a 0. Yeah.
It is plausible.
Sure, it's plausible. Absolutely, it's plausible. You could have someone who is a picture of health, right? They're rare, probably, but it's plausible, right? So how does that intercept? Does that intercept make sense? No, it doesn't make sense, which is a key to asking yourself, is this the right model for this data? Is this the right model for the data? So now I'm going to start questioning, maybe this isn't the best model for these data. How about those confidence intervals, right? Stata is awesome in that it gives you those confidence intervals. How do we interpret those confidence interval things? I like to think about confidence intervals as sets of plausible values. It's the range of plausible values. So the effect of physical health, our best guess is that for every 1 unit increase in physical health, we expect about a 1.8 increase in the number of doctor visits. But it could be as low as 1.4, might be as high as 2.2. Right? So we think about it that way. Right? It's our set of plausible values. Did anybody then do the betas?
Yes.
Okay, how do we interpret those betas there? I see a beta for physical health of, what's that, 0.39 or something like that? How do we interpret that then?
For every 1 standard deviation increase in physical health, we expect utilization to go up by 0.38 standard deviations.
Right, right. Now look at the effect of stress. Look at the relative of the size of the coefficients for stress. So, was that 0.013? And the standard, the beta for that is 168. All right? So it's difficult to interpret the coefficients, or to compare one coefficient versus another in its raw form. Right? Now when we put everything on the same scale, measure everything in the same metric, now we can see, oh, you know what, stress, which originally, if I just looked at the magnitude of the coefficients, it looks like stress, although statistically significant, looked kind of small as compared to physical health. But now when I put them on the same scale, now we begin to see the explanatory power of stress.
So based on these beta coefficients, could you say like, I mean, I'm not going to be good at math, but could you say like, if it was 0.1, 0.3, that like physical health had a 3 times the expected effect on doctors?
Holding everything. Then you can talk about the relative importance of those variables.
In terms of the interpretation, though, it's not the same as interpreting the coefficient?
No.
Okay. So
Because the units are different, right? Whereas before we were talking about 1 unit change in stress.
Yeah.
Now the unit is standard deviation. But we've standardized everything into z-scores.
Mm-hmm. And so it's not for every 1 unit standard deviation increase in physical weight. So interpreting it, it's for every 1 increase in standard deviation in physical health, you have 0.38 increase with 10 doctors.
Standard deviation.
Standard deviation. Okay.
You just have to know what the unit is. Right? That's why it's important to understand your data. What's the unit?
Yeah.
Right?
Yeah, I was just wondering, like,
Can you say that one more time?
Right, so the idea, what I'm trying to, the reason I use this crazy data set for a number of reasons, but one thing we're trying to talk about here is that to interpret the coefficients, you need to understand the unit in which things are measured. So if I were to look at that 178 for physical, that, I interpret that as is for every 1 unit increase in physical health. I think it's symptoms, as I recall. For every one unit increase in number of physical health symptoms, we expect the number of doctor visits to rise by about 1.78. Right, so now I'm saying for every 1 unit increase in symptoms, that's the unit of analysis, I expect doctor's visits, unit of analysis, to increase by about 1.78. Right?
And so for this doctor's visits, that's the right unit. So if you could have 1.78 doctor's visits.
Yeah. And now if I look at the betas, these are standard, these are no longer physical health symptoms. The outcome is no longer number of doctor visits. The unit is standard deviation units of physical symptoms. Standard deviation units of doctor visits. So I interpret that 0.38 as he did. I'm sorry, I don't remember anybody's name. For every 1 standard deviation increase in physical symptoms, I expect a 0.38 standard deviation increase in the number of doctor visits.
And that's the standard deviation of, like, if you went back to the raw data and looked at the standard deviation for doctor's visits. So say like the standard deviation was, I don't know, 20.
Right.
You could say that it was like 0.3 or 20.
Yeah. Exactly.
Basically, the beta allows you to quantify the relationship.
Yeah, it puts everything on the same metric,
Right.
and then allows you to compare the magnitude of the coefficients from one thing to another. Whereas before, if I were to compare that 0.01 for stress to the 1.7 to physical health, it would look like that physical health dominates. Oh, the really important thing is physical health by a factor of, 1,000 or something like that, or 100. When it's still really important, but when I put everything on the same scale, that domination decays a little. Make sense? Okay. So what did you guys do after you did your regression? There's lots of things you could have done. So order here isn't necessarily important after you do the regression. So think of this as your patient, right? Your patient is presenting. This is your patient, your model. What did you do?
Before we get there, can I ask just about mental health? How do you explain that it's, in words, that it's not something that it's not helping to explain?
So once we take into account level of physical health and level of stress, mental health symptoms are not a predictor of utilization.
And I came in late, sorry, but when I did bivariate correlations, the correlation between mental and physical health is 0.5.
Yeah. So how could we explain that, right?
Yeah. So those two seem their suggestion of
Yeah, they are related, right? But they're not.
So how can mental health have no impact on?
As we can think about it as once we've taken into account these other variables, the effect that mental health has, the unique contribution that mental health has on the outcome is negligible. So if we were to draw it, right, so you're bringing up the relationship between mental health and physical health, right? So if I were to draw that relationship, can somebody help describe to me how I might draw that relationship? So I have a Y here.
So if that was physical health, there'd be another circle that we overlapped.
Okay, so I'm going to call this physical.
Okay, and then there'd be a circle that would not touch the Y circle, but would touch the physical circle, like would overlap the physical circle.
But what he's saying is that in the bivariate case, mental health actually does touch the Y.
It would have the same overlap.
Yeah. So it would look kind of, sort of like that, right? Whereas I don't know if you can see this little area here. That's the unique contribution that mental health has on the outcome. Bless you. This green area here is the variability that is shared between physical health and mental health that predicts the outcome. So once I've held physical health into account, this green area goes away from mental health, leaving just this itty-bitty, tiny, tiny black area. So that's why we have to understand what it means to hold something constant. So that's suggested to me that physical health, any variability that mental health does have with utilization, there's a significant portion of that variability is also explained by physical health.
Thanks.
Okay. What'd you guys do next? Tons of things you could have done. What I did next was I looked at the variance inflation factors. And I get the highest variance inflation factor was 1.44. So that tells me that physical health and stress can predict about 69% or not 69%, about 31% of the variability in mental health. So you got that look again, so that's good. I see the look. You see the other column? It says 1 over VIF. We gave that another name. Does anybody remember what we called that? Tolerance. And tolerance is just the name that we've given, another name that we've given to the coefficient of alienation. 1 minus r squared. So the reason I know that physical health and stress predict about 31% of the variability of mental health is I simply subtracted 69 from 1. All right? Does that make sense? So in mental health, about 69% of the variability is unique to mental health and separate from physical and stress. Does that make sense?
The variability in,
So if I look at mental health, that's got a variance inflation factor of 1.44. If I look at the inverse of that, I get 0.69.
are you just looking at the variance in, like within mental health, or the variance of the effect of mental health?
No, we don't even look at the outcome when we're looking at
Okay.
variance inflation factor. We're simply looking at the relationship between the predictors,
Okay.
ignoring the outcome. We're ignoring the outcome. So that tolerance, that 1 over VIF, for the coefficient of alienation, tells me that most of that variability in mental health is fairly unique to mental health, which is what we want, right? And we have an 84 down there for stress, which means that about 16% of the variability in stress is explained by the other two factors. That's fairly low. So this is pretty good evidence of a lack of multicollinearity. Right? So with respect to testing our assumptions about our model, we seem to be okay with check. Collinearity does not seem to be a problem in this case. Right?
Sorry, so did you say that 69% of the variability of mental health was unique, or 1 minus 69?
69% is unique to mental health. Right? It therefore is unique. It is separate from physical health and stress. We want that 1 over VIF to be very high, close to 1.
How, what's the cutoff though? I mean, what do you...
0.85. If we have a 1 over VIF, let's say about 0.85, if I were to take the inverse of that, that gets me a variance inflation factor of about 8 or more. Right? So if I see variance inflation factors of like 8 or more, that's sort of a signal that you have a collinearity problem or a multicollinearity problem.
Sorry. 0.85. Okay, 1 over, gotcha.
Right?
So even if things aren't looking very collinear on their scatter plots, they still might somehow magically show up as
Magically show up. Yeah, because a lot of times in our scatter plots, you're going to have things that are overlapping each other.
Yeah.
So, right, so unless you were to have a 3D scatter plot, you were to look at the sort of the height of things, right? There are techniques to deal with that called jittering. If you want to plot and separate all of the points, you can do something called jitter the plots. And what that does is it puts random separation between the plots. So people who are at the same spot in Cartesian space, they would be separated a little bit, so you get to see the separation.
So just to go back to your tolerance cutoffs you were describing, so...
So for tolerance, I'm looking for, if I saw like a 15.
Yeah, okay.
Or
the
less.
inverse of that, like so
Yeah.
0.15.
Yeah.
Okay.
Yeah, right, because if I have a tolerance of 15, that means the other variables in the model explain 85%.
Yeah.
That's collinear, or multicollinear in that case. Okay.
It doesn't sound like you're using that first column.
I can use either one. I'm trying to explain what each of these things mean.
So I understand when you interpret the second column, but what are the word meanings of the first column?
Okay, so what do these words mean, okay? Do you understand what this is here?
Yeah.
You got that? We got
Yeah.
that. This is coefficient of alienation, which you learned a long time ago. Variance inflation factor is nothing more than the inverse of the coefficient of alienation. So how do I interpret the variance inflation factor? This variance inflation factor of 0.44 here, 1.44, suggests that the standard errors for mental health are inflated by a factor of about 44% because of the lack of independence between this and the set of other predictors in the variables, in the equation. So it variance inflation factors. So the standard errors, this is what I mean here. These are inflated by, sort of 1 minus this percent. Or this minus 1, rather. Make sense? If mental health were completely...
The 144.
Yeah. Does that make sense?
Say that part one more time about 144%.
So this, if I'm looking at mental health, I have a standard error here of 1.29, blah, 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 blah. If mental health were completely statistically independent from stress and physical health, this standard error is about 144% or 44% larger than it would be if it were independent from the other predictors in the model. Collinearity makes it difficult to see the true relationships in the data.
So I guess I'm confused by the 44%. From what I thought would be like it would be 31%.
Okay.
Based on.
But here we're talking about the standard errors.
Okay.
This tells me, right? Let's just stick with this one. 0.693805, right? If I were to, let's do it. I'm just going to do it. All right, so I'm going to regress men health on physical health and stress. From there, I get an R squared of 0.3062. It's 69 or something like that, right? Yeah, 69. 3805. 693805 is 1 minus this value here. That's where we got this number. Okay? To get this number, I simply take the reciprocal of my tolerance, which is going to give me about 1.44. With me? To interpret the variance inflation factor, what that really means is, well, look, if this were completely independent, if mental health were completely independent, this R squared would be what? 0. And then I would have 1 over 1 minus 0 is 1, which would mean the effect of the relationship between this predictor and the other variables had no effect on the standard error of that coefficient. But since there is a relationship between mental health and stress and physical health, the coefficient for mental health, the standard deviation, the standard error for mental health is increased by about 44%. It's 44% greater than what we would expect it to be if the variables were independent of each other. Does that make sense? Now, the consequence of collinearity is what happens to my t-statistic as my standard error increases. The t-statistics gets driven down. What happens to my p-value as my t-statistic goes down? My p-value goes up. As my p-value goes up, we say there is no relationship between this variable and the outcome holding other things constant. So in the presence of collinearity or multicollinearity, there could be a relationship holding everything else constant, but we don't see it. Therefore, because we have violated an assumption of the model, independence of predictors, our interpretation of the world is improper. Does that make sense? Everybody got that? So this all comes down to these assumptions that we talk about, or we have been talking about, really help you. It really comes down to the degree to which we violate these assumptions, mess up our inferences about the world. That's really what we're talking about here. Right? Okay? Okay. Well, what I have here in the handout that I hope you all have is I've now given you some sort of definitions. Outliers, leverage, influence. All right? Okay, so let's talk about this a second. We have this concept of an outlier, and by definition, something that that is an outlier is going to have a gigantic residual, a large residual, and we can quantify what large and gigantic is by doing a couple of things. We can standardize our residuals, or we can studentize our residuals. So sometimes you will hear people talking about studentizing their residuals or standardizing their residuals. What's the difference between, by student, I mean like a student t-test? What happens to the t-distribution as the degrees of freedom approaches infinity? It becomes more and more normal. So when we have 465 observations, that t-statistic is it's damn near normal. So if I were to do studentized residuals or standardized residuals, they pretty much be the same thing. Okay? All right. So anything in this case, if I were to have a standardized or a studentized residual of larger than say 2, that by our definition is a large outlier, right? Okay. So let's talk about the concept of leverage. So when you think of leverage, think of Archimedes and his lever, right? When is a lever the strongest? What makes a lever a strong lever? If the fulcrum is close to the thing that you're trying to move, and you have a very long lever, right? The famous Archimedes quote is that if I had a lever long enough, I could move the world, right? So here we're talking about, in leverage, we're talking about predictor variables that are outliers, right? So a predictor variable, if that's an outlier, that's going to take your lever, and it's going to pull your slope up or down, or could pull that slope up or down, depending on how far away that particular observation is away from the mean of the outcome. All right, so if we were to draw this, this makes intuitive sense if you've ever ridden a seesaw. It really does make intuitive sense. Right, so here's my seesaw. Right, so this is the mean of, I'm going to write this down, is the mean of my y. This is my seesaw, right? My teeter-totter. I don't know what else you call it. That, right? If I had a predictor variable that was way up here at the mean of y, is that going to change the slope much of my outcome? Probably not. It'll probably change the intercept. But in general, we don't much care about the intercepts in general, right? But what if I had an outlier here, but I was far from the mean? Now, this value has a lot of leverage because it's far away from the mean, and it can exert a lot of influence on the slope of that line. Does that make sense? Okay. So when we talk about leverage, we're talking about the outlierness of a predictor variable. And then we have the concept of influence. Influence is any variable that if I remove the observation could change the equation. Okay? So in our code here, Stata makes it real simple for us to come up with these indices that we're going to need to examine these concepts here, okay? So what I'm going to do is I'm going to use these post-estimation commands, which we've introduced in Stata Lab before. So the first thing I'm going to introduce here is if I just do predict and I give a variable name and nothing after it, this is going to give me my predicted value. So I'm going to get real creative and call my y hat variables y hat. Right? I'm not that creative. And then I want to predict the residuals, or I want to estimate what the residuals are. So the residuals are nothing more than the observed y value minus the y hat value. Right? So I can let Stata do that for me too. Now, there's a measure called Cook's D. Cook's D is sort of an index of multivariate outlierness. So I could have a variable that is both an outlier on the predictor, on the criterion variable, and has an outlier on the predictors. Right? So I can have an outlier, right, which by definition is just the outcome, or I could have something that has leverage. Or I can have an observation that is both an outlier and has a lot of leverage. Cook's D takes into account all of those things. Okay? And then I'm going to get studentize. I'm going to studentize my errors. So I'm going to turn my errors, my residuals, into student value, t-scores essentially. And then I'm going to get an index of leverage, right? And Stata is wonderful in that it hides all of that mathematics away from you. It's just going to do it for you, right? So I'm going to do those. I'm going to create new variables, and then I'm going to be able to visually inspect my model. So it's like now you have a patient that's presented. Now you're doing an examination on your patient. So now you're starting to, I don't know, whatever it is you guys do for an exam. So that's what I'm doing, right? That's what I'm doing. I got my stethoscope, my tongue depressor, whatever it is you guys do. You write down all these numbers, and then you don't look at a single number and make an inference based on a single number, do you? Should you?
Is that creating the name of the variable also at that time? So you don't have to do like generate
No.
name?
It's a good question. So before, we just had these variables in the model, right? So now I created a y hat, and it even tells you here, it's the fitted values. I created a variable called residuals, there's now a variable called residuals. Predict D for Cook's D, there's a new variable D, and so on and so forth.
But these are things that Stata knows about.
Yeah. Yes.
If you do a logistic regression, can you use these same?
Yeah, more or less, yes. Yes.
So did you have, like for Cook's D, did you have to call it D because
No,
Stata
I
recognized
could have called
that?
it
You
Rita
could have called it
or
whatever you
Gita
wanted.
or-
Okay. Right. So it doesn't recognize the variable name, it recognizes the command after
Yeah.
it as.
Yeah. Right.
But you didn't put one for y hat.
Huh? Right, so I didn't have to specify anything after y hat, because that's the default behavior for the predict command.
Oh, okay.
So if I didn't tell it anything, it knows
It's
that
gonna give you y hat.
Right. And same thing for logistic regression, which we will get into. Okay, so the first thing I'm going to do is I'm going to look at a scatter plot of my residuals. You can't see that, can you? It looks nice on my screen. And let me get rid of this. Okay. Parentheses, compounds. Okay. So let me remind you what it is that we're looking for. What's that? What have I just written down? All right, these are our distributional assumptions about error. Specifically, what I have here is my distribution of my residuals. Okay? So I'm going to do this plot, and by doing this plot, I'm specifically looking at the homoscedasticity assumption. Right? The homoscedasticity assumption says that the residuals ought to be basically randomly distributed around this zero line across the entire range of the predicted values. Do you see random scatter around the regression line across the range of the predicted values? Or do you see, on average, as the predicted value gets bigger, the error tends to get bigger? You see that? So this is what we call, or what we refer to as a classic fan-shaped distribution of errors. This is, if you're going to see heteroscedasticity, this is probably what you're going to see. So we have violated that homoscedasticity assumption.
Is this because your doctor's visits is skewed, or is that totally not related to it?
It's probably because of that, but more likely it's because we started off its low value is 0.
Okay.
Right? So why is this homoscedasticity assumption important? Remember we had a root mean square error of, what was it? It was like 9.8 or something like that. Remember that? Whatever it was, I forgot what it was. The idea here is that I have a single regression line, right? And let's say I'm at some point x, and I'm going to get some value y, right? I get some predicted value y. Remember, we interpreted that root mean square error as the standard deviation of the errors around the regression line, right? The assumption here is that that standard deviation of the errors around the regression line is constant. So that if I predict a value here, the level of precision in my estimate, y, is the same level of precision as if I measure x plus z. It's bigger than x plus z because it's bigger than this. That the precision in this estimate has as much precision as this estimate. But if I look at this, that's not true, right? What's probably the case here is this 9.8 underestimates the precision in my estimate at this end of the scale. Grossly overestimates the variability, and therefore underestimates the precision, and overestimates the precision at this end of the scale. Does that make sense? No, that's good. Right. So what I'm saying here is the scores here range from here at this end of the scale, right? As I go out here, the scores range from here to here. Therefore, the level of precision in the estimate isn't constant across the range. But that's our assumption. Homoscedasticity, equal variance.
I feel like that argues even stronger to just transform the data.
Or fit a better model. Because I would bet this is probably a Poisson or negative regression, negative binomial model. Because it's count data. But we'll get to that. Okay? So the reason that we're going through this exercise here is we sort of had this checklist of assumptions that we make about our data. And so far, the only thing that we can sort of check off as being A-OK is multi-collinearity. The homoscedasticity assumption, that's out the window. That's out the window. Okay. Oh, the other thing is, right, we have this, oh, never mind. We'll get to it. This is a plot. This looks similar, right? So this is a plot of our studentized values, of our studentized residuals. And what I've done here is I've drawn horizontal lines at 2. So the mean plus or minus 2. So what this says to me is that we grossly underpredicted or overpredicted here and grossly underpredicted up here. So we have some errors, some really big errors. Errors bigger than we would expect statistically. So these are those outliers that we were referring to. We can look at these values.
Which line was under and over?
Okay. So if we were to think about it, right? So let's think about our definition of error. It's going to be yi minus y hat I. So if that value is negative, then we have overpredicted. If the value is positive, then we have underpredicted. Make sense?
And what's the benefit of looking at the studentized residual?
Well, now we can quantify
Oh,
outlierness. We keep talking about outliers, but now we can actually have a numerical index for what constitutes an outlier.
And always at 2?
Yeah, approximately 2. So these observations, we need to begin to start thinking about, do we want to throw these out? Or do we want to examine them? Are these real values? Right? Because when I begin to see goofy things in the data based on my assumption about the world, and this is one of my assumptions about the world because this is the statistical model that I fit, there are a couple of things that could explain why I see goofiness. One thing is, our model's wrong. What we believe about the world is wrong. Or the data are wrong. What's most likely the case?
Our model.
The model is probably wrong, but the data might be wrong. So what I might do is go back and examine those data to see if those are real values, if I have that opportunity. Okay. So here, what I'm going to do is I'm going to plot a histogram of my residuals. Yeah, here's the histogram of my residuals. What do you think?
Looks pretty good.
Yeah.
Looks not so bad?
I did that too, but there's some way to the right.
Yeah, I agree. This didn't do such a good job. Actually, there's a positive skew to the residuals,
Yeah.
right?
Yeah.
Yeah. On this computer, this is the way it came out. I don't know, on my computer at home, it came out way out over here. Right? So did anybody plot a histogram of the residuals? Lie to me. Oh yeah. Of course we did. Of course we did, right? So, I don't know what the hell's wrong with this computer, but they're not normally distributed. All right, so getting back to our prediction, if they're not normally distributed, then what would tend to happen is, right? What would probably happen is, given that they have a large positive skew, right? Instead of having a nice normal distribution around here like that, what tends to happen is that the errors are probably distributed like that. Well, they are distributed like that. So what that means is that we are probably grossly underestimating the values, a large majority of the values, and underestimating a small number of the values. Right?
This is
Sorry,
what
are
comes
you over and underestimating?
I would look at the sign of the residuals.
I just want to clarify, this is what comes up on
Yeah,
mine,
on
so this
that
is not
computer.
correct.
Doesn't
There's
look,
some-
doesn't
there's a
look
lot
correct.
more
It
to
doesn't
the
look
right.
correct to you, does it? We did this the other day, and it didn't look anything like
Like
this.
this, okay.
Same data, but I don't know what the hell's wrong with that computer. All right, so we have seemed to have violated the homoscedasticity assumption. We seem to have violated the normality assumption. God, this model stinks. This data don't fit the model at all. Okay, so let's go for Cook's D. All right. What I'm going to do now is I'm going to come up with a drop, what I refer to as a drop line plot of Cook's D measures. So these are guidelines. What I'm going to talk about is guidelines. So if we're going to say if Cook's D divided by 4, this is going to be our threshold for determining whether or not our Cook's D is remarkable. Right? So what I've done here is I've come up with what I refer to as a drop line plot in Stata. This red line here is the threshold. So 468 divided by 4, whatever the hell it is, this comes to be about here. Whatever the math is.
You did it the other way, I have 4 over it.
Yeah, it's 4 over that, thanks. That's it, right? It's going to be this. So any value above this red line, I sort of flag as potential problems. All right? So there seems to be some non-trivial number of observations, and in particular, this observation seems to be a good candidate for figuring out what the heck is going on, right? For diagnosing the model.
Could you go over what this,
Yeah.
what the
Okay.
things are that are connected? with the
So
line?
here we've talked about, we're dealing in 4-dimensional space here. Right? Which is I can't wrap my head around 4 dimensions, right? So we have number of times you've been to the doctor, mental health, physical health, and stress. So how do I talk about outlierness in 4-dimensional space? I can reduce it to a scalar, to a single number. I can imagine a sphere in 3 dimensions, right? And the center of that sphere, the centroid, would sort of be the multivariate mean of those 3 dimensions. And then I could come up with a distance from that space, that 3-dimensional space, right? And I can reduce that to a single number. And I'm doing that here. I'm reducing 4-dimensional space to a single number.
The top of the line or the bottom?
Okay, so here, if these values here at 0 are at the centroid, they're sort of like at the mean of that multi-dimensional space. The farther you are away from the centroid, the longer this line will be. The more of a multivariate outlier you will be.
So each point just has a line that
Yeah.
goes down to the bottom of
Yeah,
the graph?
to 0, right.
To 0.
This line represents a distance, a multivariate distance. Make sense?
And if it's above the red line,
If it's above the
not
red line, then it's a multivariate outlier.
Wait, what defines the 3D, sorry, this is like backtracking again, but the 3D space you're talking about is defined by those characters.
Well, really we're in 4-dimensional space, but I can't conceive of 4-dimensional
What are the
space.
4
But think
dimensions? Like,
of
you
4
can-
dimensions are number of times you've been to the doctor, the variables in the equation.
Gotcha, okay,
Those are the four dimensions.
okay.
Not like a dancing group, you know?
So when I look at this, is it accurate to say that I have a lot of observations that are outliers and probably have a lot of influence on my predictor.
Potentially, yes.
Potentially,
And if
but
I
they're
were-
outliers,
yeah,
and if
they're
I remove
multivariate
them, I would
outliers.
get different coefficients.
Yes.
So this may not be a good model because
Yes.
my outliers are probably driving a lot of
Yes.
potentially.
Potentially, right?
Okay.
I would start my examination with this value here.
Right there. Okay. What about the fact that you just, outside of this clearly aberrant value, the fact that you have
Several values.
several above the red line
Those are potential problems too.
Potential.
But I'm going to start with this
with
one.
this one? Okay.
If you had a fifth variable, would it be 5/n and you'd be a
No, it's 4 as a constant. This has to do with logarithms. I'm going to not get into that.
That's always the way you
So it's
calculate
just always
threshold.
4 over it.
Yeah, well, it's funny. If you read different textbooks, different authors will give you different numbers. This is defensible. I can give you references to this if you want. Okay. Any other questions? I know, as soon as you get into multivariables, like conventional thinking goes out the window because you're really in what a mathematician would refer to as hyperspace. You're in hyperspace. You're in 5 dimensions in this case. 4 dimensions. That's a hard thing to conceive of. Right? Imagine if you had an equation with 20 variables. You're in 20-dimensional space. That's hard. Okay. All right.
Are we just ignoring the details of the code for these two things or not?
Well, the code's right there in front of you, right? The other thing that I do